Hello there, 11th graders. This is Teacher Krishna, and welcome to our physics class for week number 17. Just like always, thank you a lot for coming to our online lesson and, of course, for completing all of the assignments that you have had so far. Just like every week, log into Agilex, enter the Google Classroom, download your Word document, save it inside your physics folder, and of course, you have to name your file just like it is specified right below. And as we move, keep in mind that you need to write down the most important things from this video, so you can keep track of the most essential things and of course learn a little bit more of the topic that we are going to learn about. Today we're going to learn about topic 6.04, and of course we have to start with our end in mind, which is explain the properties of lenses and mirrors and the way light acts upon them to present a model related to what has been studied. So, just a little bit of a spoiler. The topic is a little bit longer to explain and to study, but it is simpler than it might seem to be. So just keep a positive mindset during the whole class, and after a little while that we have studied it, you will notice that the topic is pretty simple actually. It's just a little bit long. Alright, so just like I mentioned before, we're going to study the topic of lenses and mirrors. And to start, we're going to analyze a term that is geometrical optics. What is it? So watching any object through lenses, that is basically what geometrical optics is. It basically redirects the light that has previously acted upon an object. So we find lenses all around us. I can give you an example with, let's say, a telescope. That is a little bit more uncommon, but in order for you to understand a little bit more about how geometrical optics work, we can have the example of a telescope. So basically what telescopes do is that they redirect the light that they capture from outside and they change it into an image that our eye can perceive. So whenever we place a telescope and we redirect its position in order to capture the light that comes from the moon, for example, then when you put your eye on the lens, you will notice that you will get a clearer and of course magnified image of the moon. That is basically what lenses do, right? It is possible to form a ray diagram by following some principles. So we need to study the way light acts upon the kind of lens or mirror where it is going through. So we need to learn some principles later on. You need to become familiar with the vocabulary related to the topic. So please go to the section vocabulary terms from page 1 and learn the definition for each one of the words. So you will find some sort of complex words around in this topic. So it is important that you go to the vocabulary section terms in Agilex, so you can review all of the terms and of course you can have some background knowledge. And whenever we start to analyze and implement the terms from there, you have a better perspective and understanding of the same. All right? I'm going to help you with some of the most complex terms that you're going to find in there. The first one is convex lens. So what you need to know about convex lens is that whenever they receive light, they are usually going to redirect it to the center of the lens, of course. So like it's right here, you can notice that there are some rays that are coming, some light rays that are coming in a horizontal position, and once they interact with the convex lens, they are redirected to the center of the lens. And what happens with a concave lens? Well, they are going to be a little bit different, and actually when the light comes to them, they are going to redirect it as well, but it's not going to be necessarily as it appears in the convex lens. Why isn't it like that? Well, what happens with concave lens is that they have certain curves that are going to create different angles than the ones in the convex lens. But do not worry, we're going to have more examples with diagrams about how light rays act upon them and how it's possible for both of these lenses to form new images. So we're going to start with convex lens. And right now, I'm going to present to you three different situations and how light acts upon the lens. So this is the first one, ray 1, part A. So you will find part A in the red arrow that you have in the diagram. Let's analyze what it says. Light is incident parallel to the principal axis until it strikes the principal plane of the lens. All right, so you can notice that the red arrow is parallel to the x-axis that we have crossing through the object, which is the purple arrow that we have right there, and of course the lens, that is the circle that is right there in number 7. Then part B, which is the blue arrow that is found there. Light is refracted by the lens so that the light passes through the focal point on the opposite side of the lens. Something you need to notice about lenses is that, specifically in the ones that we are analyzing right now, they have two focal points. And you can see that one focal point is located at 5.5 and the other focal point is located at 8.5. So this is the first behavior of light. Notice that it is parallel to the center of the lens. So when once light acts upon the lens, it is going to be redirected, and of course it is going to go through one of the focal points. Usually we need three different light rays in order to create an image. So this is just the first one. Let's analyze the following two. Okay, this is ray number 2, part A. Light is incident so that it passes through the center of the lens, where principal plane and principal axis intersects. Alright, so just like you can notice right here, one more time, we have one light ray that comes from our object. The object, of course, is signalized by the purple arrow that you have in number 4. And the ray does not go as in the way before. It is not parallel to the x-axis that is going right through the middle of our lens. So now it has a certain inclination, and of course it goes right to the center. It doesn't go to the top. So what happens here is that it just continues with the direction that it previously had. So you can notice that it is not going through any of the focal points, but still it is something necessary to analyze. And now we need one last ray, which will be this one right here. Part A. Light is incident so that it passes through the focal point on the object side of the lens until it strikes the principal plane of the lens. Alright, so now in this case, one more time, we have our object, which is the purple arrow in number 4. And we have that light right now is going directly through the focal point that is right in front of our lens. Okay, so when that happens, light goes through the focal point that is in the front, and then it interacts with the lens. You will notice that it will generate a parallel line or a parallel direction to the x-axis that is going right in the middle of the lens, which takes us to part B. Light is refracted by the lens so that the light bends parallel to the principal axis. All right. So now we already have the 3 light rays that we need in order to create an image. But now we need to combine them all inside one graph so we can notice where the new image is going to be formed and where it is going to be located. Right here. So as you can notice in the image that we have right at the top, we have the 3 lines that we analyzed at first. The first one that is right at the top at first is parallel to the principal axis. Then when it interacts, it goes to the focal point. The second one does not change direction. It just goes from the object to the center of the lens and it continues. And the last one, of course, goes from the object to the first focal point. It interacts with the lens, and then it becomes parallel to the principal axis that we have right there. Okay, so you can notice there is a purple or most likely an orange arrow right there. So the orange arrow is going to show us where the image is going to form, all right? So right now we can notice that it is going to form right in number 10, where of course the three light rays are going to assemble and they are going to work together to produce the new image. So now let's analyze the important information that we have right here in step 3. Make final comparisons for the example regarding the image position, size, and type. Right, let's go by parts. So the image position is about 2f, since the distance from the lens to the image is about twice the size of the focal length. Alright, so what does all of these mean? Well, let's go by parts, and let's go a little bit slower so that we all can understand what it's written down here. So, the 2f is because it's telling us that it's twice the focal distance from the focal point and lens, okay? And we can notice the distance from the object at first. You can notice that from the object, which will be the purple arrow that is in number 4, to the first focal length, where we will have 1.5. All right. And what happens to the distance from the second focal point to the resulting image? We can analyze that it has as well as 1.5, from 8.5 to 10. So that is why the resulting image will be twice the length of the original object, okay? So, of course, talking about the distance from the focal points to the resulting image. Now we continue. The image size is about the same size as the object. Okay, so what happens here is that since we have the same distance from the focal point to the image, then we're going to create an image with the same size, right? Let's go with the next one. The image type is real because the image formed on the opposite side as the object. So remember that we had two types of images. We have real images as well as digital images. And when the image is created on the opposite side of the object, or where the object is located, then we are going to form a real image, just like the one that has been stated right here, right? Now let's continue. All right, so now we're going to analyze a different type of part when it comes to analyzing rays. So now this one is not a lens. This one is a mirror. And you can notice that it has a different shape. The other one was just like a circle, but now you can notice that it is like half of a circle, which is, of course, wider. And, of course, its behavior is going to change a little bit as well. So let's go by parts. Let's start with part A. Light is incident parallel to the principal axis until it strikes the mirror. And part B, light is reflected by the mirror so that the light passes through the focal point. Alright, so now, just like you can notice, and it's something that is very important to notice. Lenses are going to diffract the light. So the light is going to go through the lens and then it is going to change its direction, but it is going through the material actually. But when it comes to mirrors, mirrors are just going to reflect the light, all right? That is why we don't see that the arrows are passing through the mirror. They are just changing the direction, but like coming backwards. So in the first example, when the light is parallel to the principal axis in the mirror, then it is going to be redirected, so then it encounters one focal point when it comes back, all right? One more time, it doesn't matter if it's a mirror or if it's a lens, we always need at least 3 rays in order to create a new image. So let's analyze the following two. And this is a concave mirror. All right, part number 2. So light is incident so that it passes through the center curvature. Light does not change direction and bounces back over the same line. All right, so just like you can see right here, We have our object that is one more time signalized in the purple arrow right there. And when it goes through, or most likely when it is heading towards the mirror, you can notice that it goes through the first focal point that it encounters. So when that happens, then light is going to bounce in the same direction in which it entered this area right here. And just like you can notice, first of all, from the object to the first focal point, then it hits the mirror, and of course it comes back without changing direction. All right, now we just need one more ray to analyze. So light is incident so that it passes through the focal point until it strikes the mirror. Light is reflected by the mirror so that the light bends parallel to the principal axis. All right, so it's just like you can notice right here. We have one more time that the light is coming from our object and it is heading towards one of the focal points. But you can notice that right here, it is not heading towards the first focal point, but through the second focal point. So when that happens, and after it goes through it, then it is going to hit the mirror, and light is going to be reflected in a parallel direction to the principal axis that we have right there. Okay? Now we already have our three rays. We have analyzed them already. So now, how are we going to find the image? Well, it's basically the same as in the last one. So we just need to find the point in which the three rays we analyzed before get together, and there is where the new image is going to be formed. So just like in this case, you can notice that it is formed in 5.6. Let's analyze the important information we have right below as well. So make final comparisons for the example regarding the image position, size, and type. So the image position is between F and 2F, since the distance from the mirror to the images is between F and C. Okay, so basically what it is trying to convey right here is that we have two focal points. We have F1, which is focal 1, and 2F that will be focal 2 as well. So we can find that the image position will be right between both of them. Now the image size is smaller than the object. The image type is real because the image is on the same side as the object. Alright, so basically what happens here is that since the image didn't go any further and it is relatively closer, then it formed a smaller image. And of course, it created a real image that we are able to perceive with our own eyes. Notice something very important as well is that whenever the three rays can actually convey within each other and create an image, we can define it as a real image. But if the image that is interpreted is not formed by three rays that are conveying within each other, then it will become a digital image. Now let's have a small summary. So even though there are more rays that are captured by the lenses, only few of them are needed to form the image. Of course, we have to analyze that there are a lot of light rays that are acting upon several objects, but we only need a couple of them in order to form a new image. Now you can identify the position, size, orientation, and type of image formed from the lenses. Of course, all of this is related to the vocabulary that you already studied. Okay, now it's time for you to do a small exercise. So please download the ray tracing worksheet from page number 2 in Agilex. And of course, complete some of the diagrams that you have right there. Practice how to complete the diagrams. I suggest that you only complete one of them. I'm going to give you one example, well, two examples right now on how to complete a diagram when you have a lens and when you have a mirror. So please complete two other diagrams so you can start exercising on how to find out the distance from the image, its position, and of course how light rays are going to interact in lenses and in mirrors. So here you have an example with convex lens. So basically this is what they are going to give you at first. They don't really give you much instructions and you have to complete these exercises with the explanation that I gave you before. Remember, in order to create an image, you need to have 3 light rays, okay? And you need to make them interact as in the examples that I previously gave you. So in this case, when we talk about convex lens, we need one ray that goes parallel to the principal axis that we have right here. Notice that when they are parallel like this, the light is going to be redirected to the focal point that is right after the lens, just like this one. Okay, we have our first ray. The second ray, it has to go from the object to the center of the lens. And remember, when it happens in that specific way, then it is not going to change its direction. So it will be just like this. All right, now we just need one more. And the last one goes from the object to the first focal point, the one that is right in front of the lens, until it reaches the center. Remember, when this happens in this way, we are going to create a parallel direction to our principal axis. And of course, light will be redirected in this way. All right, now that we already have our 3 rays, we can analyze the point in which the new image is going to form, which will be right over here, where all of the rays are conveying together. And it is very important that we signalize with an arrow where in our principal axis it is forming. So according to this, it will form exactly in 13.45, let's say, okay? Of course, this is not as precise as if you do it in your notebook or as if you do it in a sheet with squares, but it's just intended for explanatory purposes, all right? So this is what happens with convex lenses. And of course, it's related to what we studied before in the example that I gave. But now, what happens if we go to a concave mirror? What is going to happen? So one more time, they are going to give you one image just like this one, and it's your job to create the behavior of the rays in order to have the creation of the image. So let's start with the first one, the first ray that is acting parallel to our object, okay? Remember, when it goes in that way, light is going to be redirected to the second focal point, which will be this one right here. All right, and what happens to the next one? So we have one more time that light comes from our object. It goes through the second focal point, and when it reaches the mirror, it is going to be redirected in a parallel position. And now we're still missing 1/3 ray, but the third ray comes from the object, and it goes through the first focal point. But what happens here is that, just like you can notice, the purple arrow is right on the first focal point. So it is not possible that light goes through it, right? So when that happens, we only need to use the 2 rays that we have in order to create the new image. So where do both of the light rays we are analyzing collide? Well, the point is right over here. And of course, remember to signalize with an arrow from the principal axis where it specifically forms. So in this case, it forms in 5.5. So what are the consequences of not having a third ray in order to form the new image? What happens is that the image is not going to be as clear as if you had the third ray we were talking about. All right, so just like these 2 examples, I need that you complete at least one for a concave mirror, and of course one for the lens. That is going to help you out to keep track one more time of the behavior of the light rays. All right, so you can go and of course complete your exercises. Once you are done, come back and we can continue analyzing some important terms. So important terms and equation. So we have focal length. So the focal length is the distance from the focal point to the center of the lens. We have object distance, which is the distance from the object to the center of the lens. And we have the image distance, distance from the image to the center of the lens. So basically you need to take the center of the lens as a reference in order to find the rest of them. So in this case, if you want to find the image distance, so center of the lens to the image. If you want to find the object distance, then the center of the lens to the object, so on and so forth. It's pretty simple. And of course, we need to analyze the equation that we have right here. This is the equation for both convex and concave lens. So we have 1 divided by the focal length equals 1 divided by the distance of the object plus 1 divided by the distance of the image. As you can notice, it's a very simple equation, and you can use it, of course, by rearranging the formula and actually isolating one of the variables from here. So let's just analyze what the terms we were learning about will look like in previous graphics that I showed you. So let's start with the object distance, and it's the brown that you find right there in brown. So you have your object, which is the arrow that you have in number 5, and you have the center of the lens, which is in number 7. So in this case, the distance of the object will be 2 centimeters. All right, now we have to analyze, which is our focal distance, which is the distance from the lens to one of the focal points. It is shown in the picture in the yellowish or orange arrow that you have right there. And in this case, we will have a focal point of 1.5 from the center to one of the focal points. And lastly, we have the distance of the image, which is from the center of the lens to the point where the image is created. So in this case, will be from 7 to 13, which will lead us to a total distance of 6 centimeters. All right, this is, of course, the lens that we're analyzing right here. And let's analyze an example with the mirror. So what happens right here? So distance of the object, of course, from number 4 to number 8, from our object to the mirror. Distance of the image, of course, from our mirror to where the image forms, from 5.6 to 8. And lastly, the focal point, from our mirror to one of the focal points, which will be from 6.5 to 8. As you can notice, it's something very simple to analyze. Sometimes you just need a little bit of logic, but it's a little bit big to explain, okay? And lastly, this is the last thing, don't worry guys. This is just one problem to explain how to apply everything we have learned. And it goes like this. An object, candle flame, is 25 centimeters from a double convex lens. Where is the image of the candle flame? If the local length of the lens is 18.4 centimeters. Just like always, it is important to list your givens, so you have a clearer perspective of what information you have and which one you can use to work with. So we have the distance of the object, which will be 25 centimeters. We don't know the distance of the, we don't have the distance of the image, but we do have the focal distance, which will be of 18.4. So now we're going to be using our equation, the one that I showed you before, and we are going to be substituting some information. So we can substitute the focal distance, and we can substitute the distance of the object. That's why we have 1 divided by 18.4 equals 1 divided by 25 plus 1 divided the distance of the image, right? So now if we rearrange this a little bit, we are going to try to isolate the distance of the image. So it will lead us to 1 divided by the distance of the image will equal 1 divided by 18.4 minus 1 divided by 25. So whenever you finish the problem, you will find that 1 divided by the distance of the image will equal 0.0143. And in order to change and actually totally isolate the distance of the image, we're going to be working on the inverse, which basically means rearranging a little bit the formula and operating that one and leaving the distance of the image alone. So whenever we finish, we will find out that the distance of our image will be of 69.7 centimeters. It is very simple. You just need to clearly understand the behavior of the light rays inside the lenses of the mirrors. And of course, you need to take into consideration the formulas, what variables you have, and which one you have to find. So, what will be your evaluation today? You have to read and summarize the topic 6.04 and complete the exercises that you encounter in page number 4. Take the quiz for topic 6.04 once you are done. And well, as it is usual, I know that you have a class like in 5 minutes, almost likely when we finish our Zoom session. So you will have until the end of the day to finish with all of this. All right. So take your time, analyze it, and I wish you the best of luck in the evaluation for this topic. So thank you guys for coming, and it's been a pleasure having you here with me. I will be seeing you next week. Goodbye.